The polygraph, or lie detector, is a machine capable of revealing the secrets of the human body, and it has become increasingly popular in different fields. But how is a device built that can uncover lies? To understand it, we head into the factories of Lafayette, where the most advanced polygraphs of today are assembled. But before that, let's go back to the beginning of the polygraph's history, an invention that went from being an experimental idea to becoming the modern tool we know today. It all started in the late 19th century with Cesare Lombroso, considered the father of criminology. This Italian researcher tested devices to measure the physical reactions of suspects. In 1895, he used a curious device called the hydrosphygmograph, a glove that recorded changes in blood pressure during interrogations. The big breakthrough came in 1921, thanks to John Augustus Larson, a police officer and physiologist at the University of California, Berkeley. He designed the first modern polygraph, integrating in a single device blood pressure, pulse, and respiration monitors. The data were recorded on a rotating drum with ink, and the device, called the cardiopneumopsychograph, debuted in real robbery cases in 1922, marking the beginning of its practical use. At the same time, William Moulton Marston, a psychologist who as early as 1915 had already developed tests to measure blood pressure, left an important mark in this field, and also linked this invention with a very popular character from comics and screens, though I will tell you more about that later. A few years later, in the 1930s, Leonard Keeler refined the invention by adding sensors to measure the galvanic skin response, which detects electrical changes related to sweating. Keeler patented his version in 1931 and brought it to market, selling it to the FBI and other agencies. During World War II, the device was used to interrogate spies, and with the arrival of the 1990s, the digital era completely transformed it, replacing paper with computer recording. Today, companies like Lafayette Instrument lead its manufacturing. So how is a lie detector built that can help solve criminal cases? Let's move to the industrial core, the production line of a polygraph. It is a meticulous process that combines precision engineering and technology, from the very first idea to the finished equipment. It all begins in the design department. In a room filled with monitors, engineers work with CAD software to model every component: circuits, sensors, casings, and fittings. On screen, the three-dimensional model is rotated, opened, and examined piece by piece. Nothing is left to chance. Screw placement, cable routing, ventilation, maintenance access, and assembly tolerances. The selection of materials is also defined here. Stainless steel for the electrodes that capture skin conductance, flexible rubber for the pneumographs that measure breathing, tough ABS plastic for the casing that protects the electronics. All under standards of the American Polygraph Association and internal specifications, with the goal of achieving reliable physiological readings, under optimal conditions, around 90% accuracy according to reference protocols. With the design approved, the prototyping stage begins. Test casings are printed, the first electronic boards are manufactured, and functional mock-ups are assembled. Here, details are corrected, connectors that must be moved millimeters, sensors that require better shielding, or cables that need greater flexibility to avoid strain. So, how does a lie detector actually work? A polygraph is not a magical truth machine, but rather a tool based on principles of physiology. Its goal is to record automatic bodily reactions that usually appear under pressure, such as when someone feels anxiety while lying. Picture the scene. A person sits in front of an examiner with several sensors attached to their body. Two elastic bands, called pneumographs, wrap around the chest and abdomen to measure the rhythm and depth of breathing. The cuff on the arm monitors blood pressure and pulse, while small electrodes on the fingers track changes in sweating, known as the galvanic skin response. In some tests, an additional sensor is added to detect sudden movements and prevent physical restlessness from distorting the results. A session can last around 2 hours. During that time, the examiner alternates simple questions designed to establish a baseline, such as, "Is your name John?" with others directly related to the case, like, "Did you take the money?" All reactions are recorded as digital graphs, and the software amplifies the data so they can be analysed with precision. The idea behind the polygraph is that lying activates the sympathetic nervous system, causing measurable changes in the body, variations in breathing, blood pressure, pulse, and skin conductance. However, the device does not detect the lie itself, but rather the stress that accompanies it, and that stress can come from many other causes: nervousness, too much caffeine, or simply the pressure of being tested. In essence, it is like an X-ray of physical reactions to certain questions. Interpreting those data requires experience, which is why only specialists trained for weeks can provide a reliable reading of what the graphs show. So how are the individual parts of a polygraph actually made? Let's start with the pneumographs, the tubes responsible for tracking breathing. Their production begins in a polymer plant, where liquid rubber is heated to about 200 degrees Celsius and pushed through an extruder that shapes it into hollow tubing. What comes out looks like long black hoses, accompanied by rising steam and the steady hum of machinery. Once cooled, the tubes are cut into segments of about 60 centimeters, long enough to wrap around the chest or abdomen of any person. The ends are sealed with heat, creating an airtight closure that preserves internal pressure. Before approval, each tube goes through resistance tests, inflated with compressed air at different pressures to simulate deep, rapid, or shallow breathing. If even the slightest leak is detected, the tube is discarded. Technicians wearing protective glasses and gloves inspect each piece under LED lighting, making sure it can capture even the subtlest changes in breathing. This is no minor detail. The frequency and depth of air entering and leaving the lungs is one of the most sensitive indicators of stress. Now, let's move to the blood pressure cuff, responsible for recording pulse and blood pressure. Its production starts on an automated textile line where sheets of durable nylon are laser cut into perfect rectangles with clean edges. Between those layers, an air bladder made of polyurethane is inserted, a flexible material strong enough to withstand repeated inflations without deforming. The assembly is done with industrial sewing machines that secure the layers with reinforced stitches, designed to endure up to 300 millimeters of mercury without giving way. Plastic connectors, made through injection molding, are firmly attached to allow connection with the air tubes from the central unit. Then comes testing. Each cuff is inflated repeatedly, simulating real exam conditions. In the control room, multiple units inflate and deflate in unison, like a group of hearts beating together. If one shows leaks, wear, or any defect, it is removed and recycled. In this component, precision is not negotiable. A failure could compromise the entire measurement. Finally, we have the galvanic skin response electrodes, responsible for detecting conductance changes caused by sweating, one of the key stress indicators. Their production takes place in a high-precision metallurgy plant where stainless steel plates are laser cut into uniform discs. Each piece is then polished until it has a smooth, reflective surface, ensuring optimal skin contact. A conductive gel coating is applied next. Its formula, designed to improve signal transmission without causing irritation, ensures the electrode captures even the slightest variations. The cables that connect them to the central unit are shielded to prevent electromagnetic interference from lights or nearby devices. These are soldered with automated precision equipment that controls temperature, timing, and exact bonding points to guarantee a durable, fault-free connection. Quality testing includes connecting the electrodes to simulators that reproduce the electrical properties of human skin under different humidity levels. This way, even the smallest conductance changes, as little as 0.1 microsiemens, can be verified. Only electrodes that meet this level of sensitivity move on to the next stage. Now we move to the core of the polygraph, the central unit. It is built in controlled environments similar to clean rooms used in the high-end electronics industry. The process begins with fiberglass sheets coated in copper, which are etched with photolithography to create circuits as fine as capillaries. These printed circuit boards serve as the physical foundation of all the electronics. At robotic stations, microprocessors, high-tolerance resistors, and signal amplifiers are soldered in place. The precision of this work is so exact that no human operator could match its consistency. This eliminates defects such as cold solder joints that could compromise the reliability of the device. Once the electronics are assembled, firmware is loaded, the internal software that controls all operations. This program is designed to filter electrical noise, amplify physiological signals up to 1,000 times, and transform data into readable graphs for the examiner. In the final stage, technicians calibrate each unit, verifying that it can record changes within milliseconds and process up to 100 samples per second. Here, all the sensors, breathing, blood pressure, and skin conductance converge into a system capable of recording and processing physiological information with high precision. Finally, we reach the housing, the outer protection of the polygraph. It is manufactured on an injection molding line, where ABS plastic is heated to about 250 degrees Celsius until it becomes fluid. The molten material is then injected under pressure into hardened steel molds, which define each shape and detail with precision. When the pieces come out of the mold, they are still hot and are cooled quickly under powerful industrial fans to prevent deformation. Afterward, the housings go through mechanical polishing with rotating discs that give them a matte black finish resistant to scratches and wear. Machines drill the cable ports with tolerances within fractions of a millimeter, and, in the most advanced models, touchscreens are integrated to display real-time information. The result is lightweight, durable, and portable units weighing less than 5 kilograms, designed to protect the delicate internal components from dust, impact, and environmental conditions. With the housing ready, final assembly begins. In a brightly lit line, the components are brought together with precision and repeatability. The pneumographs, blood pressure cuff, and electrodes are connected to the central unit using color-coded medical-grade connectors, ensuring secure attachment with no signal loss. The central unit is fitted inside the housing and secured with titanium screws, chosen for their resistance to vibration and corrosion. Then, the control software is uploaded through a USB port, configuring the system to interpret physiological signals in real time. In some models, built-in artificial intelligence algorithms automatically adjust analysis parameters to improve accuracy. The last step is the initial power-up. The screen displays calibration graphs, the sensors respond, and the device is ready for use. Before leaving the factory, every polygraph undergoes a complete verification, ensuring compliance with all technical and quality standards. Only then is it packaged and prepared for shipment, ready to be used in a real session with full reliability. Before a polygraph reaches an examiner, it must pass through rigorous quality control. In test rooms with controlled temperature and humidity, each unit is connected to physiological simulators that reproduce real signals. Irregular breathing patterns, accelerated pulses, and skin conductance levels that mimic sweating under stress. In front of high-resolution screens, technicians monitor live graphs, verifying that every channel, breathing, pulse, and galvanic response is recorded with precision. Final calibration is carried out under the standards of the American Polygraph Association, known by its initials as APA. The software is adjusted to minimize false positives, using machine learning algorithms that refine data interpretation according to operating conditions. Only the units that pass every test receive the official APA seal, a guarantee of reliability in professional environments. Once this stage is complete, the polygraphs move to the packaging phase. In clean rooms, each unit is placed inside a custom foam-lined box designed to absorb impacts during transport. The package includes technical manuals, spare cables, calibration certificates, and a basic maintenance kit. Finally, the boxes are grouped on pallets and prepared for shipment. From the factories, for example, in Indiana, shipments are sent to their final destinations: public security agencies, government institutions, private research companies, or independent examiners in different countries. At each location, these devices are ready to fulfill their role, whether in criminal investigations, employee screening processes, or even television productions that require polygraph tests. Now let's talk about some curiosities that make the polygraph even more fascinating. One of its inventors, William Marston, was not only a psychologist and lawyer, but also the creator of the comic book heroine Wonder Woman. The famous lasso of truth she wields was directly inspired by the principle of the polygraph. The idea of detecting lies is not new. In ancient China, for example, there was a curious practice. Suspects were asked to chew dry rice. If, when spitting it out, the rice remained dry, it was interpreted as a sign of guilt, since stress could reduce saliva production. In popular culture, the polygraph has made countless appearances. It shows up in movies like Meet the Parents or TV shows like The Moment of Truth, where its reliability is exaggerated to build dramatic tension. The reality, however, is less absolute. Even spies, such as Aldrich Ames, who worked for the CIA, managed to pass polygraph tests by practicing techniques to control physiological responses. Its use varies by country. In Japan, it is employed mainly in corporate environments to evaluate loyalty, while in the United States it is more common in federal agencies and certain hiring processes. There are also documented cases of people deliberately altering results, for example, by regulating their breathing or inflicting mild physical pain, such as biting their tongue, to manipulate the readings. This brings us to an important point: the reliability of the polygraph. Supporters cite accuracy rates of 90 to 98% in controlled tests, provided that modern equipment and highly trained examiners are used. Still, the scientific community maintains a more cautious stance. The polygraph does not detect lies directly, but rather physiological responses linked to stress, and that stress may be caused by unrelated factors such as nervousness, medication, or even caffeine. Independent studies place accuracy between 70 and 90%, while warning that false positives are relatively frequent, particularly in innocent but anxious individuals. For this reason, countries such as Germany and Canada prohibit its use in judicial proceedings, and in the United States it has not been admissible in most federal courts since a ruling in 1998. The National Academy of Sciences has also concluded that it is not reliable for mass screenings such as airport security checks. Even so, in well-defined contexts, for example, specific investigations or pre-employment evaluations, and under standardized protocols, it can serve as a useful interrogation tool as long as it is not treated as conclusive evidence. In every case, the human factor is critical. The honesty and expertise of the examiner make the difference between a meaningful reading and a flawed interpretation. And that is how polygraphs are made. Tell me, what did you think of this process? Share your thoughts in the comments. If you enjoyed the video, click the like button and don't forget to subscribe to the channel. In the windows you'll see next, there are more videos that may catch your interest. Go ahead and watch one. See you next time.